Thank you. My name is Kyle Reeves. I'm a postdoc working at La Maison de Dissimulation, and this work I'll talk today falls under the category of materials for energy, and it was in collaboration with Professor Mathieu Salin at Sorbonne Université and colleagues. So today I'll be talking about our investigation exploring the electrochemical properties of bi-redox ionic liquids using first principles molecular dynamics simulations. So some context is if we're interested in exploring and identifying new materials for electrochemical inner storage, we have to think about the ways in which that's done. So here on the bottom right, we can imagine batteries as a way to store energy, one that has high energy density and perhaps lower power density. So energy density is the amount of energy you can imagine per mass unit of the material. And power density is sort of the rate at which that can be expelled. So batteries, lithium-ion batteries, we have atoms that move into the electrode or interact with the electrode and undergo some sort of electrochemical process. Whereas if we move up on the top left-hand corner, we can imagine the concept of capacitors, is the idea of parallel plate capacitors, but also something known as the EDLC, or the electric double layer capacitor, in which ions in a solution separating the electrodes can migrate to the electrodes and accumulate in some amount of structure emanating away from the electrode. And so you have charge buildup, which is the source of the energy density in these materials. Somewhere in between are these pseudo-capacitive type materials, which likely have some sort of behavior of each of them, where we have migration of mobile ions towards the interface, and on the other side have some amount of electrochemical interaction at the interface once they've approached it. And these have different mechanisms of storage and experimentally have been observed and measured. And so we can confirm that, for example, if we vary the potential and investigate the current, we see a squave waveform for something that looks like electric double layer, whereas for atoms or molecules which have very specific potentials at which electrons are transferred, we have peaks at a very specific potential. And this pseudo-capacitive behavior is some compromise between the two, where we see the square-like function, but with oscillations coming from this electrochemical activity. So the goal of our work and how we take advantage of high-performance computing is to look for, identify and search for new materials which increase the energy density without necessarily compromising the power density. So that's to say to move in this direction on that plot. And so supercapacitors are proposed as one of those types of devices which can be used, which supercapacitors are essentially a way in which charge is stored at the electrode-electrolyte interface via some reversible ion adsorption at the interface. That includes electric double layer capacitors and pseudocapacitors, depending on the nature of the materials involved. And so there are two questions that we can consider. First is, for example, what is the electrochemical nature of those species, the electrochemically active species, as they approach the interface? So that is to say, can we understand and describe the electronic structure and the way in which electrons move between, for example, the electrode and the molecule? And another question on a different time scale and length scale is perhaps what are the structure and dynamics of these electrified interfaces, the diffusion of these electrochemically active materials, the nature of the interface. So today I'll talk mostly about this question on the left regarding the electrochemical properties of the molecules, but obviously this is a very important question, and I direct you to the upcoming webinar, which will be given by Professor Salin on July 7th, which looks and investigates more about the modeling supercapacitors at the molecular scale. So today I'll be just discussing the electrochemical properties, the nature of electrochemical properties, in particular of bi-redox ionic liquids. So what are bi-redox ionic liquids? It's a very particular class of molecules that was proposed by Olivier Fontaine and his group at Montpellier, in which we have an ionic liquid here in blue and in red. So we see the ion in blue and the cation in red. So we have the charge species consistent with or accustomed to with electric double layers and the migration of ions. But additionally, we have this covalently linked electrochemically active moiety. So here we have anthracene, which can accept an electron, and the tempo moiety, which is an electron donor, in which case we have some migration of charge species and then a possible electrochemical interaction with the electrode. And so the idea is that you apply a voltage potential in the device, and these molecules, these systems, will migrate in the direction consistent with the charge and the polarization of the device, moving into a porous electrode, and therefore bringing these electrochemically active molecules in proximity of the interface and encouraging electrochemical reactions to occur and increasing the amount of energy density of the system. The advantage is that regardless of the oxidation state, that is to say with or without the electron in this electrochemically active moiety, the molecules will remain charged and therefore interact with the potential applied to the device. And experimentally, this has been observed in a group of Fontaine and all observe that the specific energy of these materials doubles compared to systems without these redox active electrolytes. So it's been shown as well. So this is where our work comes in, using high performance computing, is to investigate what is the nature, what are the atomistic details of these types of systems to understand why they behave the way they do, and insights into design of future generations of these class of materials. So propose here to run molecular dynamic simulations here of cations. We see tempo, for example, the isolated electrochemically active molecule, and then two which have the ionic liquid covalently attached to it, for example, to explore the effect of this covalent linkage on the electrochemical properties, the potential at which the electron transfers occurs. And here are the anions as well, similarly having the isolated ionic electrochemically active moiety and the linked version with the ionic liquid. So we're using density functional theory molecular dynamics in particular because we're interested in having an accurate description of electron structure and dynamics in these types of simulations. And in this case, we'll run all 5 Bi-Redox ionic liquids in acetonitrile, which is consistent with the experiments that were run, 1 in the oxidized state and 1 in the reduced state. So in total, we have 10 simulations that we're investigating. And to not dwell on the details too much, I want to point out here that every half of a femtosecond, we're printing out the positions and the forces of the atomistic system as it evolves in time. So we have a fair amount of information on positions and forces for a variety of different solvation environments. I certainly won't spend a lot of time here because I realize these equations are specific to this domain, but I think it's important to point out with the metric is what our goal is. And here, this delta A represents this free energy, and it's the free energy that we can link to this electrochemical potential, the potential at which electron transfer will occur. That's for both reduction and oxidation. So we have an expression for the reduction and an expression for the oxidation. And inside this ensemble average, what we have is this delta E, or the so-called vertical energy gap, which simply put is just the relationship between the energy for a specific configuration in its oxidized form with the identical configuration, the identical structure in its reduced form. So it's an energy difference for a given structure. We can simplify it assuming certain Gaussian fluctuations. And in the Marcus theory, which is often used in a simplified version of electron transfer, we have a 2-term expression, one which is related to the delta E and one which is related to this term with sigma squared, which is related to the fluctuations. This is what's referred to as the reorganization energy. And so I point this out because this is exactly where our MD simulations come in. So we run our MD simulations, we can sample from all of the structures throughout the 20 picoseconds that we recover, and then compute what this average value of this vertical energy gap should be, and also compute the fluctuations in those energy gaps to come up with some free energy. So that's how we're going to approach this and use our thermodynamic integration mechanism to get information about the electron dynamics themselves. Once we have these values of free energies, we can ultimately use them to construct something, these free energy wells, which give descriptions of how energy changes given some reaction coordinate, for example, the oxidized surface and the reduced species. So we can imagine as the electron transfer occurs, it will move up in energy, experiencing some barrier, and then moving into the, for example, oxidized to reduced species. So we can recover information about the activation energy, so the amount of energy it takes to overcome that barrier, as well as this reorganization energy, which is related to the solvation. So we have information that relates to electrochemical properties with the specific atomistic details of the simulation as well. So normally, given a group of chemists, I would present all the results. But knowing that we're a mixed group of scientists, I won't spend too much time focusing on these results. And if you are interested, I've noted the publication for these results at the top, so you're welcome to peruse that. But really to emphasize that the role of high performance computing is to run these from my perspective, long simulations. 20 picoseconds is a long simulation for first principles, which requires a self-consistent loop to converge electronic structure before moving on. But to recover some somewhat limited information about the electrochemical properties. So that includes, for example, here this lambda, which I said is the reorganization energy or the information about the solvation. We can look, for example, between our tempo, and as we link the ionic liquids, what we see is that there's a decrease in the reorganization energy. That suggests that there's some difference in the way that solvation plays a role during the process of electron transfer from tempo to tempo plus, for example. And it's different as we add this linker. So it is something to consider that the solvation structure does change as we change the ionic liquid. But overall, if we take a look at the free energy, we notice that it's very similar. And in particular, because this decrease is compensated similarly in the change in the average energy difference. So that is to say, we can begin to explore and investigate the ways in which these electrochemical properties vary, and ultimately also go back to the atomistic details of the simulations and look at what is possibly contributing to that as well. So given the nature of this talk is somewhat more broadly related to computing and taking advantage of computing, instead of exploring those specific details, I've elected to talk about some of the more recent work that we're exploring to be able to take full advantage of these simulations. So the large amount of positions and forces that I had mentioned before we print, are there ways in which we can take advantage of those to get even more information or to extend other tools that are possible to describe these supercapacitor systems? So as I mentioned, there are definitely advantages to using DFT level simulations. The DFT level electronic structure is particularly important because this vertical energy gap is an electronic phenomenon, this electron transfer to the other. So we'd like to have, so it's essential to have an accurate description of the electronic structure of these materials. The advantage of DFT as well is that there's no need for parameterization. You could make the argument there's a choice of exchange correlation functional, but there's no fine tuning a priori to the simulations, and we can launch them and perhaps test the effect of exchange correlation later. The disadvantages is that, as I mentioned, I had said 20 picoseconds is long for me, but in the reality, there are simulation methods for simulating these systems, which can go for much longer. And I'll discuss that in just a moment. So we're limited to a relatively short period of sampling in the systems, and also limited in the complexity. So obviously, if we're interested in exploring porous electrodes and the ways in which these molecules, as they intercalate into the electrode, interact with its local environment in a porous system, we'll be definitely limited in that regard as well. So can we move forward identifying new approaches that takes advantage of these simulations that we've already generated and looks to use creative uses of more high performance computing? And one of those tools is classical molecular dynamics. So similar to DFT, density functional theory molecular dynamics, these classical molecular dynamics advances the system atomistically over time, but instead of using a density functional theory to compute the electronic structure and then to compute the forces as a result of this distribution of electron density, there are analytical expressions which can be used to describe the interactions between atoms, and those analytical expressions can therefore be used to compute the forces also between those atoms. And so the step about computing forces and how the system propagates is much faster, and therefore allows us to compute more complex systems and for longer times. So it's a very attractive approach because we can begin to explore systems that are a bit more realistic with respect to real-life devices. And this has been done, for example, when looking at electron transfer in solvated ions, for example, iron 2 and iron 3. Classical molecular dynamics has been shown to be an approach that is possible to describe these types of electrochemical processes. So what we propose is in fact, it's a bit of a buzzword, but it's interesting nonetheless, I think, to explore the potential of using machine learning and artificial intelligence, in particular artificial neural networks, to take advantage of information we already have to predict a value we're interested in. So, for example, we have a lot of information about the structure, dynamics, and forces of our system. Can we construct a machine learned model, an artificial neural network that allows us to predict electrochemical properties? That'll require us to, first of all, improve the force fields, those analytical expressions which describe the interactions, in order to have and recover structure, dynamic, and forces which are consistent with both the DFT level simulations, but more broadly speaking, the real what we might be able to experimentally observe as structure and dynamics. And the second part is optimizing and exploring the architecture of the neural network itself. So the idea is that we take the simulation trajectories that we've already generated, and we have the DFT calculations already from having computed this vertical energy gap. I had made a point to note that the vertical energy gap is sort of that metric, the energy between a structure between the oxidized and the reduced state, so before and after the electron transfer. We have those data already, having completed the study, and so it can serve as our reference to the predicted value that we use to train the model. So the DFT calculations will be used as the reference, the real value, and ultimately to be able to take any structure that we can recover, push it, feed it into the neural network, and predict an energy, energy gap that can be then related to the electrochemical potential. So currently, as I mentioned, we have all of the data from the DFT simulations, but in theory, these structures could come from any simulation. So we can imagine running classical simulations, which sample from a larger amount of phase space, different solvation structures, which can influence electrochemical properties, and use those structures and forces, feed them into the neural network that's trained with the DFT, and come up with approximations and distributions, which can then be related to the electrochemical potential. The predicted values, as I mentioned, are the vertical energy gaps, but in theory, we can add other output nodes into the neural network as well. So we could say, for example, things that we can verify and measure using DFT for the charge on the atom, on a specific atom, for example, or the dipole of a molecule for a given configuration. Those are all things that potentially could be integrated into this approach as well and predicted. Once we decide on the architecture, though, every time it needs to be retrained. And so it's worthwhile to take into consideration what it is that we're interested in before we set it up and train the whole molecule. Maybe that goes without saying. So feature engineering, what do we feed into it? We have a lot of data. You could just increase the depth and the complexity of our artificial neural network and hope that it learns itself. We, at least to test this initial approach, decide to pre-process the data, which includes the positions and forces as they are in Cartesian coordinates, computing bond angles and dihedrals. From a sort of chemical intuition, we suspected that these might play a role in the properties of the electrochemical properties of the molecule itself as well as the solvation environment. So the distance from the center of the electrochemically active molecule to the solvent molecules themselves, as well as the solvent orientation. So these are some of the hyperparameters if you're interested in how we set it up. It's a relatively simple, for the moment, artificial neural network, which is why I'm not calling it a deep neural network. But these calculations for the test were just run on my local machine. So we can imagine how it's not terribly expensive to be able to relate the data we've generated to this prediction. So as a preliminary result, you can see if we take 500 snapshots here of DFT, this is what we computed for our study. And so these are DFT level accuracy, this blue curve here. We feed the positions and forces into our neural network, and we have a set of predictions for a set of structures that the model has never seen. And we see that there's a distribution of green and energy gaps, which when fit with the red curve aligns relatively well. But of course, there's always the fear of overtraining. So we then followed up on is investigating if we feed classical MD simulations. I have a colleague who ran classical simulations of the same system. We drew on numerous structures from those simulations, which presumably sampled from other spaces, and tested it. And we see that, in fact, while the mean is in good accordance, here in 0.02 EV, the reorganization is a bit off, but only by an error of 0.07. So in the interest of time, I'll point out where we're going next. We're looking to extend molecular dynamics by being able to couple classical simulations, for example, to sample different structures via artificial neural networks to get information at the DFT level about the energy gaps and therefore relate to electrochemical potentials. We are interested in finding different sources of the structures and using that as a feedback mechanism to fine-tune force fields to be able to replicate structure in vertical energy gap relationships. And finally, to be able to visualize and understand what the weights mean in order to have some physical insight as well into the system. So here, this will hopefully allow us to explore more realistic systems that include confinement and interfaces, can be translated into investigations of thermoelectricity, which, as mentioned before, is one of the tasks in the materials section, as well as more complex systems that have mixtures and ultimately have influence on electrochemical potentials. So with that, I'll stop now, and I'll thank you for your attention, and I'd be happy to take questions.
Thank you very much, Kyle. We have 5 minutes for questions if anyone wants to ask one.
Hi. Hello. Can you hear me?
Yes, Alessandro, we can hear you.
Yeah. Thanks. Very interesting talk. I just wanted to understand. You mentioned the reorganization energy due to the environment, to the the electrolyte, I guess.
Mm-hmm.
I was wondering about the internal energy reorganization, if you want, or whatever happened to the molecule that typically change internal degrees of freedom, I mean, due to charging or discharging.
Yes. So if I understand your question. So for example, if we imagine, let me find an example, we can imagine sort of this anthracene, which is normally planar. And you're saying, for example, if there's a bending mode, we would expect a difference in energy as that molecule bent. Is that right? Am I understanding?
Yes, as it charges.
Yeah. And so a part of this expression, which I quickly ran through, is that these energies that are related to the internal differences should be captured because these are computed at DFT level. So for example, in our simulation, we'll take a snapshot from the simulation. Obviously, we have the energy for one of the oxidation states. We take the identical structure, and we change the charge of the total system to be able to compute the energy difference. And so therefore, anything that's related to the internal degrees of freedom should be captured in that energy difference. And so I would say that's the majority in this first term here, where we then see the solvation effects more so in the second term. And this, for Marcus theory, is at least normally distributed because of some randomness or normal distribution of fluctuations in solvation environment. So if I understood correctly, I would say most of those should be captured in the DFT calculations, and predominantly are in this first term here.
I see. Okay. Okay. Thanks.
Okay, if there's no one else, then Kyle, thank you once again. I will stop the recording now.